First of all, I'd like to thank everyone for joining us for this hour-long seminar. The seminar has been organized between NASA and the NRC within our early career networks under the umbrella of the EFAR organization, EFAR being the International Forum for Aviation Research. EFAR was initially founded as a chance to create more of a collaborative approach to aviation research across government institutes. And this is an excellent showcase of that goal, because we have 4 excellent speakers from our 2 organizations sharing some of the research that they've been working on, and hopefully getting a chance to find more opportunities to collaborate in the future. So with that introduction, I'll now pass it off to my
looks like Taylor froze. But that is okay. He was about to pass it off to me anyway, just for a little bit of housekeeping rules. So we are going to have a lot of people on this call, so that we're going to ask to make things run as smoothly as possible to please keep your cameras off and your microphones muted. After each presentation, there will be an opportunity for you to ask a question. When that is the case, use the raise hand function when prompted, and we'll be moderating those questions. But you can also post questions and start discussion in the chat. So again, thank you all for being here, and I'll just turn it over to our first speaker, Dr. Faezeh Razi from the NRC. So Faezeh, if you want to get us started.
Okay, so let me just share my screen. You can see it?
Yes.
Okay. So hello, everyone. My name is Faezeh Razi. I'm research officer at Gas Turbine Lab in NRC. And today I'm going to talk about a novel test rig for boundary layer ingestion propulsion studies. This is a collaborative multidisciplinary project with different partners, both from Europe and Canada. The design of the fan was done by GKN and KTH from Sweden, and Bombardier and the U of T has some consulting role on this project, and we are very thankful for their great contribution. Now I'm going to give a brief introduction about the topic. You know that minimizing emissions and noise of aircraft propulsion systems is very important, and recent advances in aerospace propulsion seek to minimize them via electric hybridization. Unfortunately, aircrafts are fully suited to electrical propulsion, as the energy storage requires significant weight increases and making them considerably less efficient than liquid hydrocarbon fuel powered propulsion systems.
Wow, that's crazy.
That's Chinese.
So benefits due to hybridization can only be realized if coupled with other energy-saving technologies such as distributed propulsion or integrated propulsion airframe systems, as shown the concepts in these pictures. One such energy-saving technology getting attention is boundary layer ingestion, or BLI, in which the boundary layer developed over the aircraft is ingested by propulsor. In a conventional engine installations, a propulsor is normally installed under the wing in order not to ingesting any boundary layer over the aircraft. However, for BLI engines, the aim is ingesting those boundary layers, so they are closely integrated with the fuselage. A BLI propulsor consists of a fan that's powered by an electric motor, which in turn is powered by the main engines in most of the concepts. And the BLI propulsor reduces the fuel burn in 2 ways. One is that the aircraft has a less weight dissipated, and also the other is the BLI concept has a higher propulsive efficiency. If you see equation 1, which is for the conventional engine, the free stream velocity is V0 that enters the engine, and Vj is jet velocity that exits the propulsor. This equation is modified to equation 2 for a BLI concept, and here the velocity entering the engine is V1, V1 is velocity inside the boundary layer, which is normally less than free stream velocity. So this is why, based on this equation, you can see how the propulsive efficiency would be higher for a BLI engine. So, but with these effects, the same net force requires less power or energy by the propulsors, and this results in having less fuel consumption. Preliminary studies on the benefits of BLI predict up to about 10% reduction in aircraft energy consumption. However, there are very limited experimental results in publications compared to many safety or analytical studies. So this is why NRC developed a test rig capability for studying BLI propulsion. And this test rig is kind of unique because it can operate at high altitudes and Mach numbers, but it is scaled down in size. There are several architectures for BLI design, but in current projects, based on our partner design requirements, we are evaluating an axisymmetric or aft-mounted BLI design, similar to the one shown in this picture. The initial purpose of the test rig is to demonstrate whether, in fact, BLI is advantageous in reducing the power required for a given thrust, and this is achieved by creating minimal boundary layer and thickening the boundary layer in front of the fan and comparing the required power for a specific thrust. The second purpose is to validate the performance of BLI fan concepts, and this is achieved by measuring flow properties at different sections along the fan which operates under BLI condition. Here you can see the picture of the test rig setup. The boundary layer facility consists of altitude planium, boundary layer generator, and fan rig, and it is designed to simulate a propulsive fuselage BLI. The altitude facility is a depressurized steel duct system, and the duct is comprising a bell mouth inlet, and downstream of that there is a throttling valve which adjusts the pressure inside the planium. Downstream of that there is a section for flow conditioning screens, and then through this contraction section it connects to the test section, and then downstream there is a exhaust pipe which connects to the air compressor. The air compressor can create a negative pressure inside the planium in order to simulate the high altitude conditions. So this altitude facility is capable of providing altitude up to 12 kilometers from sea level. The boundary layer generator is designed to simulate the boundary layer developed over the aircraft. It is a center body that located inside the test section, and it is supported by some struts. The aim of having this strut is to simulate the effect of vertical tear or engine pylons on the real aircraft. So this contour related to total pressure that analyzed for the real aircraft, which is here Fokker 100 aircraft. And the aim is to get the same pattern at the fan inlet by having these struts in the test rig. So the boundary layer can be created from this center body naturally due to skin friction. Also, this comprises an array of perforated plates through which the pressurized air can be blown off and manipulate the boundary layer thickness at the fan inlet. The fan is a 1/7 scale, and it's located inside the skeleton nozzle, and it is designed to operate under distortion patterns. And it is powered by a 3D-phase electric motor, which is located inside the center body. This motor capable of providing power up to 20 kilowatt and a speed of 36,000 RPM, and it is cooled down using both water cooling and air cooling loops. The instrumentations are mounted on 5 linear traverses traversing through different sections along the fan. And all these sections can be also rotated to plus and minus 180 degrees in order to map the whole flow field here. There's a bypass section here that allows the boundary layer that generated on the outer wall of the test section can pass through it without being ingested with the fan in order to be more similar to the free flight condition. The power of the fan is measured both from electric power as well as using torque that is measured by load cell. And also a speed sensor is located in front of the rotor to measure the speed rotor. So different parameters and also thrust are measured in order to evaluate the performance of the fan. Design of the test rig was done using some safety analysis. Some modifications was applied in the test rig. For example, there are some modifications on bypass section and also on the number and shape of the nozzle struts in order to make shape of the more streamlined to have the flow feed everywhere in the test section smoother and more uniform. In the design part, the other part was bundle layer generator design. So to do that, some pilot testing was conducted in aerodynamic lab using some flat plates with different pattern of holes. And the bundle layer thickness was measured in different places downstream of that. And the aim was capturing the relation between the bundle layer thickness and the velocity passing these holes. So this concept was used to design the bundle layer generator over the center body. And some safety analysis was conducted to evaluate the effect of different patterns as well as the effect of varying mass flow rate or velocity through the bundle layer system. Testing was conducted in 3 phases. The first phase was tunnel calibration. In this phase, only empty tunnel was used for calibration, and the calibration performed by varying velocity and altitude. And the aim was to calculate the calibration coefficients from calibration curves, and also using phytostatic probe and traversing inside the test section, the uniformity of the flow at the test section was confirmed. Also, the turbulent intensity at the test section was measured using hot fire anemometer, which was calibrated at different speeds and altitudes. The second phase of testing was bundle layer generator calibration. The aim of this phase was to develop a relationship between upstream mass flow or pressure altitude and the bundle layer generator mass flow and the bundle layer thickness at the fan inlet. So by doing this test, the bundle layer profiles were measured over multiple circumferential points in order to evaluate the uniformity of the bundle layers. And also the profiles generated by bundle layer system was evaluated against target profiles from safety predictions. So here you can see just a few results from this phase. For example, the effect of different hole patterns are compared at one specific condition. There are velocity contours, and here is the effect of varying bundle layer mass flow rate on bundle layer thickness, which is the average of 8 circumferential positions. And there are some error bars here which showing the standard deviation. So just comparing results show that the configuration with these smaller holes upstream would be the best option because it gives the smallest variation in bundle layer thickness around the circumference. So this configuration used for the further testing with the fan installed. The third phase or last phase of testing was fan testing. The test conditions are summarized here. The pressure altitude varied from 20 kilopascal to 95 kilopascal. The motor speed varied from 40,000, which corresponds to 45% of aerodynamic design point of this fan, to the 32,000. Bundle layer thickness varied from natural to 95% of a span for some cases. And also the nozzle blockage added as shown in this picture for some conditions that we are approaching a stall. Because in that conditions, the mass flow rate through the test rig would be very low, and this results in some flow reversal through bypass section. So this is required to add this nozzle blockage. The data analysis of this phase is still under process, but I just provided some preliminary results to compare safety analysis with the experiment for some specific condition. This top picture is the total pressure contours at different sections, and the bottom ones are from experiment. And also there are the velocity profiles at different sections for some angular positions. They are compared with CFD. Comparing this result overall gives a reasonable good matching between CFD and experiment, and also the effect of those struts or top and bottom wakes are observable from both profiles and contours. As another example, I just provided the effect of boundary layer thickness on the result. The left-hand side shows the velocity contours at the fan inlet for some specific phase with a natural boundary layer, which has the thickness of 60% of a span, and with artificially increasing the boundary layer to 95% of a span. And you can see the effect is obvious from the contours. Also, to show the effect of increasing boundary layer thickness on fan performance, here two plots are shown for the effect on thrust to power ratio. The left one is for at constant speed and changing the pressure altitude, and the right one is for constant pressure altitude and changing the speed. In all plots, the first points are related to natural boundary layer. So you can see increasing the boundary layer first has some positive effect on fan performance that results in increasing thrust to power, but it is to some extent. Then increasing more the thickness of boundary layer gives some negative effect. So this is kind of interesting result and conclusion, but it needs more evaluation, and we're gonna have more analysis on aircraft level as well. So deliverables and future opportunities about this project can be summarized here. By doing this project, we can create an integrated technology demonstrator of boundary layer ingestion. We understand the technology gaps that need to be overcome to implement this technology into aircraft. This project serves as a testbed or proof of concept for future full-scale engine BLI studies, and also gives the capability to do further testing with the current testing, like investigating the effect of different BLI fan design, as well as, for example, investigating the effect of rain, hail, or ice ingestion. Thank you so much for your attention, and if you have any questions or comments, please feel free to ask, or maybe contact me through my email address. Thank you.
Thanks, Faezeh, for that presentation. I actually had a question. So when do you think this sort of technology will be mature enough to be brought to market? And also, when do you think you'll be able to do like actual flight tests of this technology?
Mm-hmm. Yeah, so now some testing is conducting both here, and I know NASA has like a very the big wind tunnel for BLI. So they are now in this stage, and so there is very, long future for this to be implemented on the aircraft. So different like companies, especially gas turbine companies, now started to change to hybrid electrification, and BLI is one of the important and main part of that. So I can say like for next 5 or 10 years, this technology would be, integrated on the aircraft.
Perfect, thank you. So we actually need to move to the next speaker, but if you guys have more questions for Faezeh, you can put them in the chat. And Faezeh, if you want to post your email, if people want to contact you afterwards in the chat, that'd be great.
Sure.
So thank you. And we're actually going to move on to our next speaker, Dr. Brodan Richter from NASA Langley. So Brodan, if you want to take it away.
Yes, good morning, good afternoon, and good evening to everyone. Can my slides be seen? Okay, and can you hear me okay?
Yes.
Okay, so let me switch the presenter. Okay, look okay still? Okay,
yes.
Well, great. Okay, hello everyone, my name is Brodan Richter. I am a research materials engineer at NASA Langley Research Center. I am in the Advanced Materials and Processing branch. and today I will be talking about computational materials simulation of additively manufactured microstructures. So first, a little bit about the powder bed fusion additive manufacturing process, which is the process of focus for today. So on the right is an overview of the process here. So overall, the process works off of basically the concepts of spreading powder, melting that powder, and repeating that again and again and again and again until you build up a large bulk scale part. So powder spreader here spreads powder from the powder reservoir, some type of energy source, whether it's a laser or an electron beam, melts the surface really quickly. That solidifies a layer and that repeats. Some of the advantages of the powder bed fusion additive manufacturing process are that it enables really high design complexities, and that ties into the next advantage, which is also very high feature resolution. The energy sources can usually be focused down to on the order of tens to hundreds of microns. And that combined with the high controllability of the laser and the layer by layer nature of the process allows you to design really complex parts that can have complicated internal cavities. Also, an advantage of the process is the ability to do near net shape creation of parts. And that's because of the fact that you can import a part from some type of CAD file and print it almost directly as is. This then overall allows for potential reductions in tooling, since you no longer have to start from a large cast billet and then machine down or maybe roll it and do process after process. You can just print the part directly as is. And this then helps provide low concept to production time. You can think up some new design, you can send it to the powder bed fusion machine, get it printed and go take a look at it, see if you need to make changes and really reduce that prototyping time and concept to production. Now, some of the disadvantages of the process, though, are that it generally has low build speeds. It's really best for low to medium runs because of the fact that it has this really high resolution and the layer thicknesses are often about 20 microns. So you need a lot of layers to form a large scale part. And at the same time, then there's also a disadvantage of the part size. You can't ultimately usually get too large because of the size of the powder bed is usually limited to a foot by a foot or maybe a bit bigger. And you could create larger sizes, but then you also have other things to consider like residual stresses. Also, at the same time, powder bed fusion parts can often have poor fatigue performance, as well as performance and uncertainty, which I'll get into a little bit more. Now, overall, though, there's a lot of complex interaction of various different types of physical phenomenon occurring in powder bed fusion. So here shows an example of high-speed X-ray imaging of the process. The top portion is a powder layer and the bottom is bulk material. So it's a video. It's going on the scale of microseconds. So the laser is infrared, so you can't see it, but the laser starts hitting the surface. It melts the surface. The powder starts melting. The bulk material starts melting. The powder starts getting incorporated into the surface as it's molten due to surface tension. At the same time, there's gases that are put off because of vaporization. This blows the powder around. All these things are interacting at once. I'm going to play it again here. So laser hitting the surface, this melt pool cavity forms right here. Powder is getting absorbed into the general melt pool. Fluid dynamics and surface tension is causing this inertia to bounce the melt pool around. So overall, there's this simultaneous interactions of multiple different phenomena going on. There's gas dynamics, there's fluid dynamics, there's powder effects, there's phase transformations, there's heat transfer that's going on, and more. Now, all of this is then occurring constantly for hours or days because the builds, depending on the size of the part you're making, can take 22, 36 or longer hours or longer to print. This then means that during the build process of a part, there are thousands or millions of melt events that are occurring to make that final part. Now, these many melt and solidification of events cause bulk scale effects to occur for powder bed fusion in the microstructure. So this shows an example of some of the development mechanisms for that microstructure. So the process is characterized often by the formation of large columnar grains that are orientated in the build direction. And this is because you have subsequent melt and solidification events that cause the grains that are most favorably orientated to slowly outcompete with unfavorably orientated grains and grow larger and larger and larger. This, at the same time with forming these large columnar grains, can also cause very anisotropic microstructures. So here shows an example that as the thickness of a part gets thicker and thicker and thicker, you get a stronger and stronger 001 crystallographic orientation in the microstructure. Now, why is this important? Well, these anisotropic microstructures have very significant performance and isotropy in the mechanical performance of these parts. So here shows an example of fatigue tests for two samples that have been built. One of them is stressed in the direction perpendicular to the build direction, and one of them is stressed in the direction parallel to the build direction. You can see that depending on the direction that you're stressing in, the fatigue life can be almost an order of magnitude lower for one case versus the other. Overall, this uncertainty and the dependence this uncertainty has, which is based on the orientation of the part in the build chamber, makes the qualification and certification of parts made for aerospace usage quite difficult. Two different manufacturers could produce the exact same part, and if it's orientated slightly differently in the machine for when it's built, due to the just choices made in shipping the part to the machine, that could cause the performance to be completely different from one to the other. So this is caused by these thousands of interacting melt events. So how can we best understand this effect on the final part performance and try to help control it and start reducing that uncertainty? Well, one thing that is becoming very common for additive manufacturing and building understanding of the process are process structure property frameworks, or PSP frameworks. That involves using process modeling. Here shows an example of a finite element thermal simulation to feed into macro or microstructure modeling. This shows an example of Spark's microstructure modeling that then is fed into property models to try to estimate what the stress will be in the final part that is built. Overall, the goal of this type of framework is to try to help enable process control and optimization, because now you can better link processing parameters to the final properties of your parts. My focus and the discussion for this talk today is on the macro and microstructure modeling portion in the middle here. So there's various different microstructure modeling techniques for additive manufacturing. I'll just be focusing on two of them today. One of them is the phase field method. This works by simulating the microstructure development by the solution of governing partial differential equations. Now, this technique has a nanometer size resolution typically. It's very high accuracy, but at the same time, it's very computationally expensive. It can predict very fine details, such as the texture development. So right down here showing these dendrites that are growing from a solid to a liquid with two different crystallographic orientations. And at the same time, it also has a strong physical basis to it, depending on the formulation of the equations you use. In contrast, another technique is the Monte Carlo method. Here shows an example of an experimental versus simulated Monte Carlo, or an experimental sample and a Monte Carlo sample. This method works by the simulation of the microstructure through a series of probabilistic flips. It has typically closer to a micrometer scale resolution, and it's very highly flexible. You can adapt it to try to incorporate a lot of different things. At the same time, it's very cheap, especially compared to the phase field method, computationally cheap. But it has a much weaker physical basis, where the phase field method can be reduced to analytical solutions for the solidification front. The Monte Carlo method cannot, because of how it works off of the probabilistic nature. My work is trying to leverage these two different models to help produce advanced composite models that can have advantages of both of them while reducing some of the limitations of both of them. So the kind of high-level overview of what this looks like is trying to use micro-scale phase field models to feed into bulk-scale Monte Carlo models. A little bit about how this would look is that the phase field modeling has a very strong physical basis, while the Monte Carlo models have weak physical basis. So we're trying to use the phase field models to help better tie the Monte Carlo models back to physical reality in both a spatial domain and temporal domains. At the same time, the phase field model has a small domain size, while the Monte Carlo models have large domain sizes. But the phase field models can also predict very fine resolution details because of that. When the Monte Carlo method is very flexible and adaptable, and you can add and seed new features such as pores or segregation that you could predict with phase field models. So we're also trying to utilize the Monte Carlo models to attain high domain size simulations that can then feed in those higher details from phase field models to try to have both of those strengths while avoiding the weaknesses of either. The overall goal is to try to create improved bulk scale Monte Carlo models that then incorporate fine resolution features from phase field models. This is to help provide improved structural models that will ultimately provide improved performance models for how the parts perform. And this is to help provide better relation of the actual processing that is done to the final part performance in order to understand, control, and optimize the AM process. Some examples of this are shown now. So this is on crystal orientation evolution modeling. So competitive grain growth is one of the things that contributes to the bulk scale AM microstructure that you have. Now we can get really drastic speed improvements by implementing the phase field aspects in Monte Carlo models. So on the left shows an example of a higher domain size Monte Carlo model of competitive grain growth, while on the right is a phase field implementation of competitive grain growth. So you have two different crystals with different orientations shown. So the model on the right, you can see that it's a much higher detail than the one on the left, but it has simulation time in hours. And that is because it's trying to solve these stiff partial differential equations simultaneously. Well, on the left, the Monte Carlo model is much faster. The example shown here is a time of seconds, and that's because ultimately it just is weighting the flipping based on the energy of sites and whether or not having certain orientations will have more energy or less energy than other orientations. Another example of this is simulating a moving laser melt pool. So during powder bed fusion, a laser scans, melts the surface. For alloy solidification is solute field controlled. So phase field modeling allows modeling the dendritic growth alongside the solute field segregation that occurs. So on the right shows an example of the moving laser heat source, and on the left is the solute field that is splitting into regions of high solute and low solute. So you see here the yellow grain is outcompeting the blue grain as it goes along and overgrowing it. You see over here you have regions of this microsegregation that occurs that depends on where you are in the melt pool. Well, this takes hours to simulate on high performance cluster GPUs to do a 2D domain of 100 microns by 200 microns. And largely that is because of the speed of the laser and because of the fine resolution the phase field model needs to stay physically tied. In contrast, we can use the Monte Carlo model, which does lose the ability to model the solute field, but we can calibrate it using the phase field model to account for its effects to help enable very drastic speed and domain size improvements. So here shows an example of simulating temperature field and grain orientation field. And this, in contrast, is a full 3D domain that I'm only showing a cross section here. This takes only minutes to do on a laptop single CPU. So it's way faster. You can do much more simulations, much better understand the sensitivity of the laser parameters to the final microstructure, while still trying to capture some of the high fidelity effects that you get from the phase field models. So to just briefly summarize the work and a little bit about the process. So in powder bed fusion, there's many complex interactions occurring, many melting events. That these melting events ultimately impact the bulk scale microstructure, and this creates an anisotropic microstructure that makes qualification and certification of aerospace parts difficult. Process structure property frameworks are one way to help enable process understanding, and I'm working on trying to develop composite structure models that leverage the strengths of multiple models into one. So this work was supported by NASA's Aeronautics Research Mission Directorate's Transformational Tools and Technologies project, and thank you very much. Any questions?
Yeah, Brodan, thanks for that awesome presentation. Something that I was thinking about, so this computational material simulation that you're doing, is this model for a particular set of alloys, or is it just a general model to cover the behavior of most metallic alloys that you would encounter for aerospace applications? I would think different alloy systems, you'd be dealing with different melting temperatures and also different grain microstructures.
Yeah, that's a really good question. We right now are focused on titanium, Ti64 specifically. However, the frameworks are really generalized that as long as you know the thermophysical properties of the different materials and you know what standard build conditions would be, or you want to test standard build conditions, you can simulate them. So as long as you have a strong enough understanding of the material parameters, you can simulate them using this framework. However, we are right now focused on aerospace alloys of interest, primarily Ti64. In the future, I think we do have some interest in also aluminum alloys, and there's some separate work starting to get spun up on Inconel as well.
Okay, great. And then one final question, like a follow-up to that. Have you validated any of this modeling with testing on, for example, Ti64 or another alloy?
Yeah, that's also a really good question. So right now we're in the stage of collecting that experimental data. The experimental data you need to calibrate these models is unfortunately relatively lacking in the literature. You need not only examples of really high quality micrographs of the microstructure that are at a from an AM build, you need them at a variety of conditions that are sensitive enough that you can get differences in the microstructure, but not so large that you're in completely different regimes of processing. And so we're right now working on generating that to validate these models. So that is ongoing work right now.
Okay, yeah, thank you. And thank you again for this awesome presentation. So we're going to move on to our next NRC speaker, Mr. Hamidreza Yazdani. So Hamidreza, if you want to go ahead and get started.
All right. So hello, everyone. I'm happy to be here and be able to present our work to you guys. So my name is Hamidreza Yazdani. I'm research officer at the Aerospace Manufacturing Technology Center located at Montreal. Today, I will be speaking to you about Bioinspired tough ceramics. So the first question is why Bioinspired ceramics? So what's wrong with ceramics that we want to move toward Bioinspired? So as you probably know, ceramics have so many advantages: high thermal stability, low density, high stiffness, high compressive strength. However, they generally suffer from brittleness, which can limit the range of application where high toughness is required. So our goal in this project is to come up with the tough ceramics that we can control also the stiffness of the system. So what we do, we look at the nature. With borrowing some ideas from nature, we can overcome this drawback of ceramics. For example, both tooth enable and glass sponge skeleton, they are ceramic-like material, and they could overcome the inherent brittleness by using stiff and strong building blocks and architectures with weak interfaces. So in these materials, the stiffness and the strength come from the building blocks, and the toughness mostly comes from the architectures with weak interfaces. So there are so many building blocks in the nature that we could mimic and come up with the tough ceramics. So I'm going to show you a few of them that we have worked on. But before that, I want to show how we manufacture these ceramics, because no matter what type of building block we use, we are using only one type of manufacturing for now. So our manufacturing is that we use a picosecond laser available at the NRC to engrave or cut like different type of building blocks. For example, here you can see a hexagonal one that we mimic from nacre. So we engrave or cut, for example, here hexagonal shape on a ceramic sheet, and then we laminate these laser engraved ceramic sheet with the thermoplastic polymer. For example, here we use Cerulin interlayers. And then we vacuum bag the whole structure. We put it in the oven for 5 hours. And at the end, we have our like multi-layered ceramic structures. So we started from mimicking nacre. Obviously, we start from hexagons. And we were thinking that let's find the optimal length for hexagon. Optimal from this point of view, we want to increase the energy absorption of the Bioinspired ceramic versus plain one. The plain one is the same multi-layer ceramics without any shape. So we manufacture hexagonal ceramics with 2.5, 5, and 10 millimeters. And then we perform a low velocity impact test at 3 different locations to evaluate the toughness and stiffness of the system. So let me show you some results here. So you can see here the energy absorption of the hexagonal with different hexagon length versus baseline. And we can see that, for example, hexagon length with 5 millimeter can absorb energy more than the baseline. However, the stiffness of the our Bioinspired ceramics is lower than the baseline, which is normal. But don't forget that not necessarily having low stiffness is like a bad thing. It depends on the application. if we need some flexible ceramics, having lower stiffness can help the system. All right, so here you can see also the X-ray of the hexagonal ceramics versus baseline, and you can see the failure in a hexagonal ceramic is more confined compared to the baseline, and you can see that in the baseline we have some crack propagated up to the edge, and the failure is catastrophic. So after finding out that, all right, okay, all right, so we also perform some digital image correlation. Why? To find out the failure and toughening mechanism that play role in these systems. For example, here you can see that for the architected ceramics, the crack propagated through the weak interfaces. However, as I mentioned, for plain ceramic, the crack is straight up to the edge. So you can imagine that the length of the crack in the architected ceramics is longer than plain ceramics, and that's one of the reasons that architected ceramics can absorb more energy compared to the baseline. And on top of that, because we have Cerulean below this ceramic, the energy absorption, the plastic deformation of the Cerulean also is much more for the architected case compared to the baseline. All right. So the second phase is that we say, all right, so we found the optimum length for hexagonal length. So do we really need to cut through? Do we need to 100% cut ceramics? Because you know that when we cut material, we're losing a stiffness. So we wanted to control the stiffness too. So we were thinking, let's not cut through. So we have one case 100%, and other cases 40 and 70% of each tile thicknesses. And let's see if we can like improve the energy absorption or toughness, and also control the stiffness of the our system. So again, we manufacture the same the hexagonal length with different cut depth, and perform like a low velocity impact test at 3 different locations. And you can see here the result. And actually, we show that 70% cut depth architected ceramics can absorb up to 220% much more energy compared to the baseline. So not only we could increase the energy absorption compared to the 100% cut depth, obviously we increase the energy absorption and toughness compared to the baseline. And as you can see here that I'm talking about the third impact. So the system has multi-hit capability, so it can carry at least 3 impact compared to the baseline that you can see here. And also we use a different type of NDE to again evaluate and understand the toughening mechanism behind these systems. For example, we use X-ray or X-ray penetrant to find out the number of cracks or crack lengths that happening in the system. To measure the damage area, we use like infrared thermography or stereoscopy images, and we show that the failure in Bioinspired ceramic is more confined compared to the baseline. The second phase, we said, so we found the optimal hexagonal length, 70% cut depth. But if we look at the nature, they not like even nature is not really ordered hexagons. So what if we go toward stochastic or disordered hexagon by mimicking, for example, armadillo here? So what we did, we develop a formulation, and we come up with the parameter delta, which delta can vary from 0 to 1. You can imagine when we move towards 0, we have more stochasticity, and when we go toward 1, we have like ordered hexagon. Let's say for delta equal to 1, we have exactly ordered hexagonal ceramics. So what we did, we manufacture ceramic structure with different delta. It means different stochasticity. And we perform again 3 low velocity impact at 3 different locations. And we show that actually when we have a system with high stochasticity, we can absorb energy, not even more than hexagonal one, but obviously more than the baseline. Here also you can see, let's say, how they look like when we have more stochasticity or when we move toward highly organized hexagon. And you can see again that, let's say, the crack propagation in for the baseline or plane case is again straight up to the edge, but let's say for stochastic is more zigzag and is goes toward like the weak interfaces between ceramic type. So because we know the crack likes to be more stochastic disorder, so that's one of the reasons that stochastic ceramic can perform much better than hexagonal, because the nature of the crack. All right, so I want to talk to you more about other cases that we evaluate and we mimic from the nature. For example, one of them is beetle skeleton. So as you probably know, the skin of the beetle is like fibrous composites, and it starts from like 0 and 90-degree inner surface, and when it moves to the outer surface, it has some helicoidals. It means that the fiber, as we go higher, the fiber rotate with a specific angle. So we mimic the same structure, and we design like different type of helicoidal that to obtain the optimal theta angle is a pitch angle. Also, we manufacture cross ply 0-90 degree, and also hybrid one that we have 0-90 degree on the top and helicoidal on the bottom. Obviously, we have the baseline. And after the manufacturing, with the same manufacturing method that I showed you guys, we perform Sharpie impact test, and we show that actually hybrid design, the design that exactly mimic beetle skeleton. We have like cross ply at the bottom and helicoidal at the top. With that, we can improve the energy absorption of the structure. So again, you can see that we really can control the stiffness. So we can look at the application, we choose the energy absorption, and also we choose something like the stiffness of the system that suits the application, our applications. Or last not the least is the suture ceramics. So this time we mimic the white tail deer structure of the deer. And here you can see the deer has like some intel-like structure that can help the deer to absorb or to dissipate energy. So what we did exactly, we mimic the same structure, and that we call it like suture ceramics, and we perform like tensile test, and we showed that all right, so the suture ceramics can absorb more energy even compared to the other type of other type of architected ceramics available in the literature. Right. So thank you, everyone. I just want to thank my amazing colleagues at NRC, like Dr. Backman for his expertise in experimental mechanics, Mark Genet for NDE, Dr. Gholipur for his expertise in the laser machining, and Dr. Behnam Ashrafi to lead this project. Thank you, everyone.
Thanks, Hamidreza. So there's actually 2 questions from the chat, and they're closely related to one another. So the first one I'll ask is what testing method is used to evaluate the stiffness? So I'll let you answer that one first, and I'll ask the next question.
Yeah. So well, let's say when we do impact test or other type of test, we obtain the force displacement curve, right? So the area under force displacement can give us the energy absorption capability of the system, and the slope of the force displacement can give us the stiffness of the structure.
Okay, and then the other question from the chat asks, what about the influence of the adhesive in the stiffness and also the strength of the material? Do you test different ways of bonding the layers and evaluate the influence?
All right. So what we evaluate is different type of thermoplastic, like we use Cerealine or other type of thermoplastic EVA to find out the most like effective adhesive in the structure, right? So we found that, let's say, the Cerealine is the one that is give us the highest stiffness. So the story is that we want to take these like adhesive, they have high energy absorption capability. So we want to take the fully advantages of these structures. So we have to come up with the design that we can have some confined crack propagation. So this crack propagation leads to like plastic deformation of adhesives. And during the manufacturing of our structure, like we come up with a smooth and constant manufacturing method that we make sure that the bonding between adhesives and ceramics is it's fully bonded, and there is no, let's say, delamination between adhesive and ceramics before performing mechanical test.
Okay, yeah, fantastic, super interesting. Thank you for answering those questions. So yeah, we're gonna we'll move on to our last speaker, but certainly not the least, Jonathan Hernandez from NASA Langley, who's going to talk about lunar dust mitigation.
Awesome, and I just realized that my mic was on mute. Okay, let's get started, everyone. Just one moment while I bring this up for a hot minute. All right. Don't you just like when technology likes to fail on you at the last minute, right?
Oh yeah, it's the greatest feeling.
Absolutely, absolutely. Okay. Let's see. Can everyone see my screen?
Yes.
Awesome, awesome. Hello, everyone. Good morning, good afternoon, good evening, wherever you are in the world. My name is Jonathan Hernandez. I am a mechanical engineer at NASA's Langley Research Center. I've worked at NASA supporting the Advanced Materials and Processing branch as part of a member of the National Institute of Aerospace since April of 2021. And today I'll be talking about an overview of the Lunar Occupation Dust Surface Separation Technologies project, also known as LO-DuSST. Before I start the presentation, I just want to start by talking a little bit about myself, where I'm from, as well as acknowledging the massive group of people I work with. So a little bit about me. I got my degree at NJIT, the New Jersey Institute of Technology, working at studying mechanical engineering. My focus in my bachelor's was mostly on metallurgy, machine design, and manufacturing processes. Before I started here at NASA and at NIA, I conducted research on thermal photovoltaics, focusing specifically on nanostructures and the composition of metal alloys as well. And past my fun little world here at NASA and at NIA, I love to travel. I'm an avid hockey and soccer fan, and if you give me an egg everything bagel, we'll probably devour it in a single minute. So a little bit about me and a photo of myself as well. In one of my favorite spots in the whole world, which was the Suture baths. Definitely a really nice place to see out in San Francisco. And this is the team I work with. We are a amazing, collaborative and diverse group of people, ranging from chemists to electrical engineers. You name it, we have it. The majority of the team is here at Langley, so I want to acknowledge them all: Chris Woll, Lopadas, Val Wiesner, Keith Gordon, Glenn King, and I. We also have a couple people at Glenn and at JPL as well. And I'll explain what they do in just a bit, since this is a very multifaceted project. So why why tackle the problem of LO-DuSST? So we didn't know what the lunar surface would be like until we actually got there. And that was one of the more interesting challenges that NASA's had ever since having the desire to return to the moon with the Artemis mission. And lunar dust, because of the way lunar dust is created and the regolith, it poses a significant hazard to the mission and to our astronauts as well. So think about it this way. Lunar dust is produced in part because of the volcanic eruptions on the surface, and also because of the of impacts on the lunar surface. And because of this, we have these very jagged, sharp, very fine forms of dust on the surface, all over scattered. And when inhaled, this becomes a significant hazard towards the lungs, and is very abrasive in nature. And chemically reactive. So when we have a multitude of this dust just interacting with whatever you think of, it will eat away and rot onto the material. So as we look for a more sustainable presence and a more sustained presence on the lunar surface, especially with NASA's plan to return by the middle of the decade, this becomes an even more greater issue as we hope to stay on the surface for not just days, but maybe weeks or even months to come. As we've noticed, since lunar dust is a very serious issue, we kind of had to ask ourselves, how and where do we need to mitigate dust from adhering and becoming an abrasive component into our work and reducing the amount of time our materials and our equipment can last. And this is a plethora of places where we need to mitigate dust, whether it's on our EMUs and our spacesuits, to airlocks, solar arrays especially. Even things like excavating equipment all have to take some sort of consideration when dealing with lunar dust adhesion, and as well as the wear and tear. And this is where, when we look at LO-DuSST as a whole, we need a multifaceted approach to the way we reduce lunar dust adhesion, and also find ways to mitigate it from becoming an abrasive material that destroys our own equipment. So there are a multitude of approaches, and we could branch them off into two different sets. We could look at the active approach, which is where we look at elements such as dust lofting and solar panel protection. Also, taking advantage of the electrostatic properties that lunar dust has with van der Waals forces, and using these forces to create a repulsive effect and to push dust off of our equipment or our solar panels. This is where we looked into integrating piezoelectrics and other active technologies. But we also need to combine these active technologies with passive technologies. And this is a lot of our focus here at Langley. We focus a lot on surface and topographical properties, mechanical properties of different sets of polymers, metals, ceramics. And we're basically using the idea of characterizing new properties and new materials to get an idea of what would provide a more effective solution in reducing lunar dust adhesion and providing a more mitigative factor. Now, the more interesting part about LO-DuSST is that LO-DuSST really loves to interact with other projects here at NASA. So when we look at how LO-DuSST will affect other projects at LARC and at other centers across our network and our agency, we have vehicles like Viper that would rely on lunar dust. We also have an understanding of plume surface interactions, and the understanding that when a rocket lifts off from the lunar surface, we will have a significant amount of plume being produced, and that plume can be at a significant speed. I believe we were looking at 2,000 to 3,000 meters per second. I could be totally wrong on this, but with that significant amount of speed and the amount of dust that can kick up, it could become a very dangerous situation for our astronauts, which is why we have to rely on new technologies in the LO-DuSST program and others to really protect our equipment and our materials. We also have, and this is something I've worked on significantly over the past couple of months, projects like LSMS, the Lunar Surface Manipulation System. And these projects need to rely on LO-DuSST technologies to help propel dust off of their equipment. And this has become a more important situation as well, because we can't just repair things as easily on the moon as we can here on Earth, and sending new equipment is not going to be easy. So this is where our technology and our research will be essential for the sustainability of these missions. So when we kind of investigate the needs of each of these projects, we have to have an understanding of what is especially needed. We can go as far as to say we have to remove as much dust as possible. And this would be the case for solar panels, where you need the electricity fed from light to keep a whole station running. But you can also go as far as to say we can find ways to allow dust in an environment and tolerate it as well. So, for example, on the right side of the slide, we have just fresh paint, and there's exposure to dust. We can find ways to mitigate it and allow dust to interact with it, but mitigate it in a way where the materials will be able to tolerate it and it won't be an issue. So there's a myriad of solutions to go with lunar dust, and making sure that with our understanding of lunar dust, we could find materials that can either go as far as to mitigate it, and we would have to find both active and passive solutions, or we can go as far or as little as to say, well, we have something that would work just enough. And that's one of the biggest challenges we have here with lunar dust, with LO-DuSST in general. So some initial designs that we worked on, we had, for example, a deposition chamber that we started using for just an initial representation of what we wanted to do, and to get an idea of how certain materials worked in general. It was sort of a qualitative analysis of our work rather than a quantitative analysis, and it was just to get a gauge on what we had so far and to see where we can move from here on out. So for the first experiment, we just had something very simple. We had we had this huge beaker flipped upside down, and inside we had a funnel that would have dust, and we would just shoot compressed air up through the nozzle and into this little cone that had dust. The dust would basically expose itself into this environment, and it would fall onto our materials. And then we would basically look at those materials and see how they would interact. We wouldn't really use too much compressed air. And we've adapted this to look even further with more versions of our deposition chamber, like the one you see on the right, to really get an idea of how dust will interact with other conditions, including heat. Another experiment we also developed a while back here was this testing chamber that was in atmosphere. And we would have a sonic wand with our material, and that material would be covered in dust, in a stimulant. And what we would do is have the sonic wand oscillate back and forth, and we would count the amount of particles that would fall into a particle counter, which is that yellow box you see in the second photo to your right. And that particle counter would allow us to see, would give a quantitative analysis of how much dust we were able to repel with some sort of oscillating motion. Again, this is also a initial and a more preliminary analysis of understanding lunar dust adhesion, and then moving forward from there, we could have an understanding of how things would work. And then also, this is a little bit of the future work that we plan on doing. When we talk about lunar dust, the biggest concern has always been about plume. When we have plume being expelled in that ejecta, that could be a very great concern for a lot of our equipment on the lunar surface, and having that plume interaction going up as far as 2,000 meters per second can be a very dangerous situation. So having an understanding of how we could experiment that is something that I've been working with for quite some time. onto the right side also, we could also look into how the legs of lunar landers can be reusable, because we wouldn't want to swap each of these legs more often. So LO-DuSST would allow us to kind of, with the new materials we develop and understand and incorporate into these technologies, would allow us to build onto that and incorporate more feasibility and sustainability on the lunar surface. And some of the ways that we hope to incorporate that come from new testing mechanisms. I know that one that I'm developing is helping incorporate a vacuum chamber into our experiment, and combining a multitude of different testing standards, such as Tabor, and using that to our advantage, and providing an environment in which we could, in a sense, replicate the lunar surface here on Earth. Not fully, but to a significant degree. And just a little bit to kind of just talk about the next steps and moving forward here. One of the biggest, as we've discovered with LO-DuSST, the most crucial part with LO-DuSST is to really incorporate an entire suite of technologies, passive and active, that can truly help us keep a sustained presence on the lunar surface as we phase out from low Earth orbit with the International Space Station and moving towards Gateway and presence on the lunar surface. So our focus is going to be establishing benchmarks for wear studies, promising scalable techniques that we can incorporate onto our mission, as well as developing new coatings and materials for solar panels and dust lofting applications. This is a really exciting piece of work to be involved in, with and there are many facets of how this can be approached. And we have such an amazing team here at LARC, at Glenn, and at JPL getting this done. I wanted to thank them all, as well as the Advanced Materials and Processing Branch, the Research Directorate at NASA, Langley, as well as all of you for attending this presentation. It's been great having here all of the speakers here. This has been a really great group for everyone. And if anyone has any questions, feel free to ask. Thanks again.
Thanks, Jonathan, for that presentation. I'm wondering, do you already have a lunar mission identified that you want to fly this technology on, or is that something for a later date?
It is something for a later date, but the idea is that overall this could be something that could be incorporated towards any mission, to be honest. So a lot of the technologies that, like, for example, I did mention LSMS, that was something that we were looking to work with. And the idea is that this isn't just this could be a one size fits most approach towards all aspects of Artemis. So the goal isn't for one particular mission in one particular mission or one particular rover. It's for everything, and that's the whole goal of LO-DuSST, to really become a new applicable solution for lunar dust adhesion mitigation.
Great. And then there's another question actually from the chat. Says, what types of coatings are you working on for passive mitigation?
I know the biggest ones we've been looking at have been ceramics. Our focus, we haven't really, I can't really say what specific types of ceramic coatings we've worked on, but I know ceramics have been a big talk, just because of the way they can handle great levels of abrasion. Think about your car brakes. A lot of people are now moving towards ceramic brakes just because they're far more durable and last longer amounts of time. So we're looking into the world of ceramics, especially. I know Val Leisner has really pushed that a lot. But also, in a sense, understanding our substrates as well. So maybe we could develop newer substrates that may work more effectively and go hand in hand with those coatings and those polymers and the ceramic coatings. Those are all critical things that we have to look at. So I would say definitely the ceramics have been quite promising so far, but there's still more work that needs to be done. And that's where my job comes in, to find a more permanent solution into testing and finding ways to benchmark wear, especially for a lunar environment.
Okay, perfect. Yeah, thank you for that answer, and thank you for this awesome presentation, Jonathan.
Thank
So
you.
yeah, that's actually the end of our program today. I want to thank all of our awesome speakers from NRC and from NASA again from taking time out of their day to present. I hope everyone here enjoyed the topic. Everyone should have posted, well, I think most people have their emails posted in the chat. So if you want to continue discussion with our speakers, you're more than welcome to contact them. But yeah, this recording should be posted soon, either emailed to you or we'll post it in a general repository for you guys to share. But yeah, thank you so much for attending, and I hope you guys have a great day wherever you are.